Okay, welcome again, everyone. In this presentation, we will discuss briefly about our ongoing developments for Lehigh FIU hybrid wind simulation technology that we're trying to develop and have it available for external users who would like to use the two NHERI facilities. I'll be presenting this talk with Liang and Thomas. So starting from like where we are in terms of wind engineering, why we thought that our next move should be like real-time hybrid simulation. So current state of the art, let me use the pointer, is that for like very iconic, let's call it iconic structures or different structures, different infrastructure that was not tested before or analyzed before, we typically do wind tunnel testing, and we discussed before that we can get pressure coefficients over the surface. We can also assess their dynamic response with aeroelastic testing. So these are the typical wind tunnel testing. There are different wind testing facilities, wind tunnels or open jet like the wall of wind facility. We can also use CFD simulation. I must say for wind tunnel testing, the limitations are there, and they are basically about the scaling, because when we scale down like larger scale structure like this, a big structure like this to a smaller scale like model, we are missing some of the real wind impacts on the structure. And it would mainly affect the peak forces or the peak pressures acting on the structure. Once you scale it down to a typical like length scale in a wind tunnel, it could be 1 to 400, for example. So it's as small as that. With CFD, of course, the limitation are the computational cost. Also, validation with wind tunnel testing or field measurements has been challenging for CFD community. So we still, like from wind engineering perspective, because I'm more like on the experimental side, we still see some uncertainty with the CFD simulations. And like the general tool is to do finite element modeling, combine that with wind tunnel data or CFD data to run analysis. So again, the simulation of finite element model would give you the ability to consider nonlinearity of the material, which is something that we cannot consider in wind tunnel testing or CFD simulation. But also it's missing something very important, which is some aeroelastic effects, like what I discussed earlier about the aeroelastic response of the structure. So how the structure will be deflecting under this wind, how the forces will be different under this certain deflection or excitation. So it's something that we are missing if we combine finite element with wind tunnel or CFD data. And this is why we try to add that great technology, real-time hybrid simulation. It's been there for earthquake hazards for a long time. And now it's time to bring this technology and this expertise to wind tunnel testing. Again, the advantage of having real-time hybrid simulation, first of all, that we can enable more large scale testing by testing like substructure of the model, which means that we can eliminate possible scaling effects that change or affect the accuracy of the results. We can also capture nonlinear effects if we combine that with numerical modeling, like what Liang was discussing. We can consider simulations of wind structure interaction like better at larger scale, which means that we can better understand wind-induced response, aerodynamic damping effects using larger scale experiments. So again, this brings us to the larger scale testing. Recently, we've been also thinking about combining different hazards. So combining wind and wave. So for example, at the wall of wind, we cannot simulate wave. But what we can simulate is that if we have a certain actuation system to simulate the wave motion of the structure and how this would affect the wind profile and then the wind forces acting on different structures. So this is another application that we can think of. So we can study multi-hazard effect. And back to the scaling issue, just to give you some numbers to understand how the scaling effect is very important in wind tunnel testing. So this is a typical drag Reynolds number plot for cylinder structures, like let's say conductors. As you can see, for Reynolds number of full scale, which is in this range, 10 to the power 6, the drag coefficient is something like here at this red line intersection. While when we small that down to like a smaller size, and the Reynolds number can be as small as 10 to the power 3. So it's less in Reynolds number in order of magnitude. The drag coefficient is completely different, as you can see, which the drag here is the force acting on this structure. So these are the numbers, like for example, if you have velocity of 50 meter per second, a diameter of 2 meters, then the resulting Reynolds number is in the order of 10 to the power 6. If we scale that velocity to 1 to 10, so the velocity now is 5 meters per second, diameter is reduced with that length scale 1 to 500, so the diameter is like 4 millimeters, then the Reynolds number is significantly reduced. And to overcome this issue, for example, here there's an example of Burj Khalifa building tested in Western Ontario with a very small scale, like 1 to 500. Again, this is typical scale, it's not too small. But to see the effect of scaling, they needed to go for 1 to 50 scale model for this portion of the structure. And not surprisingly, but the results showed like 20 or 25% difference of forces acting on this model compared to the larger scale replica of it. And again, this is like the drag coefficient plot can give you the answer why. Now, the challenges of real-time hybrid simulation in wind tunnel testing are basically about the frequency or the time. So if we think of like a smaller scale test with that length scale 1 to 300, a typical velocity scale of 1 to 500, doing the math between the length and the velocity, one can get the time scale of 1 to 60, which means that 1 second in wind tunnel represents 1 minute at full scale, which also means that if we divide that over like 1 over that time scale, we can get that 60 hertz in wind tunnel represent only 1 hertz at full scale, which means that the model is going to be very fast compared to a full scale model. So the numerical simulation to accommodate this, faster process may not be fast enough. That's one challenge. Also, the actuators to apply deflections on the physical substructure may not have like adequate frequency response. And I'll leave Liang and Tommy comment on these. So the advantage of having larger scale, for example, if we go from 1 to 300 to 1 to 20, keep the velocity scale 1 to 5 means that the time scale now is much better, 1 to 4, which means that 1 second in wind tunnel represents 4 seconds at full scale. 4 hertz in wind tunnel represents 1 hertz at full scale. So there is an improvement of doing larger scale testing. And this is why the rule of the wall of wind as a larger scale facility comes in. We have like long discussions with Lehigh to select how we start or where we start. And the idea was that let's first develop the algorithm, develop the technology of real-time hybrid simulation in the wall of wind using Lehigh expertise and their equipment, and see where are the challenges, the lesson learned, and how we can improve that. Okay, so we selected this case study of tall buildings with rooftop mounted antennas or monopole, which you can find it in many different areas around the world. Liang, I think, discussed or showed this building so many times. So this is the 40-story building we're gonna use, and we will just assume that this building has a rooftop telecommunication tower at the center. Phase 1, as Liang discussed, was about aerodynamic testing. So we first wanted to see what is the wind forces acting on the surface of both the building and the monopole. We completed that at a scale of 1 to 150. which is a little bit small scale to the wall of wind like typical testing. But again, we wanted to accommodate this size of the structure. We obtained pressure coefficients and contour plots on the surface under different wind angles, mainly 0 and 90 degrees. Liang, would you like to discuss about the real-time hybrid simulation? Yeah.
So, well, maybe Amal, you can help me to go for next slide when I say it. So for the first phase, as I presented before, the FIU built a rigid building models, and we obtained the wing pressures, and we gotta use this wing force as a predefined wing load, and we did hybrid simulations. And we gotta use this one as comparisons between the aerodynamic model and the rigid model. So what we did is we did a 3D real-time hybrid simulations using this predefined wind load. And Amal can go next. Okay, so for the phase 2, right now is our currently working stage. We gotta do real-time hybrid simulations with aerodynamic models. We are aeroelastic model, yeah. So where we had is, instead of only using the 3D, Amal, you want to go for it? Yeah. So instead of only using the 3D 40-story building, we want to consider. We also build the aeroelastic models in the FIU wind tunnels, where we can impose the displacements or the experimental response to the building models, and also capture the wind force based on the experimental substructures, and feed it back to our simulation coordinators, and to calculate the real-time hybrid simulation response. Therefore, you were able to see the difference between the aeroelastic models and the rigid model. And if you can go next.
In the next few slides, I will discuss more about the aeroelastic model of this building and monopole structure.
Yes. And in here, for the aeroanalytical substructures, we are building models in the computers in Lehigh, and the experimental substructures, we gotta build this in FIU tunnels. And the phase 3 is in our planning stage. As I talk about, since we have the viscous dampers in our lab, we could also do a real-time hybrid simulations So using the nonlinear viscous dampers in this in the buildings, see how the nonlinear viscous dampers can help the structural vibrations, which typically means the reducing the accelerations using the aeroelastic models in the FIU wind tunnel test. So basically, in the Lehigh facilities, we have experimental and analytical substructures, and the FIU wind tunnel, we have the aeroelastic model, and we gotta run the real-time hybrid simulations in the same time.
Yep. And I also must say that in phase 4, we are thinking to go with the larger model for the monopole, so we can assess the scaling effect, again, using hybrid simulation. And in these next few slides, I will discuss about like our current efforts on developing these aeroelastic models. So we are planning to do full aeroelastic model for the building itself, using mass stiffness techniques to represent the dynamic properties of the building, while the monopole dynamic properties will be simulated by selecting or appropriately selecting a cross section that represents the dynamic response of this monopole. This will be like phase 2 part 1. Phase 2 part 2 will be implementing real-time hybrid simulation with this aeroelastic test, where we remove the spring mass damping apparatus and then add the actuation system to represent the displacement and deflection of the building in the 2 directions. So as I mentioned, we have springs representing this global stiffness of the building. We are simulating the first 2 modes, and we are assuming linear modes. Mass, lumped mass, located at specific location under the joint or the bearing here. So it can represent the generalized mass of the structure, and also damping using like either oil or magnetic field, electromagnetic field. We did some finite element analysis to assess the design of our system. So we got very good matching between the target frequency and the selected cross sections and the frequency of the resulting model. As Walter mentioned in the tour, the wall of wind tour, the actuation system and the stiffness, the masses, everything will be underneath the turntable. So the building only will be exposed to the wind above the turntable level. So this is the 0 level, basically. The actuation and everything will be underneath the turntable. So we are designing currently this box apparatus, thanks to my PhD student, Haitham Ibrahim. We'll skip that. We also selected the actuators. Tommy will discuss about that in a few minutes. This is just a quick visualization of how the actuation will be working together. We have two actuators moving in two directions, simulating the along wind and the crosswind displacements of the system. Okay, Liang.
Yeah, so here is just some key features on the analytical substructures. In here, instead of it's similar, we have a BRB frames in the east and west directions with outrigger columns and BRB frame in the middles. We're also adding 40 meters multiples in there. We have around like 2,965 elements. And still, so all these elements are nonlinear explicit four-space fiber elements. So this is what we gotta do for the hybrid simulations. Amal, you can go next. Oh, that's Tommy.
Oh, okay, yeah. So we had provided like an overview, graphic of like what the configuration is going to look like in the wall of wind. Very crude drawing. I'm not good at drawing, so I just wanted to show like the overall architecture of this, where we have our Simulink real-time system with an actuation system and having the building model. And all of this with it's going to be developed in there. So if you go on top of it, so the actuator will be below the turntable. So this is an older image. I just put it in there for reference. So you go to the next. So the idea is that with the fans turned on, you have the wind loading going into the system that's being fed into the real-time system the way we are going. I'll explain how the integration of the wind data is going to go in, but then we'll have a response of the numerical model and synchronization with the physical model at the time step that it's required. So next slide. All right. Okay. Yeah. I'm sorry. Just the format got me. So what are the challenges for real-time requirements for real-time hybrid simulation? That we have to solve this equation of motion in real time. We talked about this using the explicit unconditionally stable methods. How do we interface with the wall of wind data acquisition, the scanner valve system, and do that in real time? Because typically the wall of wind does not do that. They don't interface with it in real time to do any analysis. They record the data and then later on look at it post-process. Next. And then how are we going to impose displacements to the aeroelastic model? Aeroelastic model to that's the physical substructure in the wall of wind. So how are we going to do that using actuation? All right, so those are our challenges. So first, we use our how we solve an equation of motion. Next, we use that Simulink performance real-time system, that dedicated kernel for doing that analysis. And so what's our next challenge for the IT? What equipment do we need? That's fine, you can leave that. You have the scanner valve system with the ZOC 33 and DSM devices. Those devices are what acquire the pressure tap data and condition them. So we need to interface with those. And then now we have to introduce some actuation and using some sort of controllers. So these are the hardware components that we have to interact with and interface with. So next. So the DSM 4000, the first challenge we had was to figure out how are we going to do this, do something different than the wall of wind FIU was familiar with. So what did we do? How did we get the data from that? Next is we use the SpeedGoat in real-time Ethernet capabilities. So the DSM 4000 is an Ethernet capable device, and we're able to connect to that in real time and capture at 625 hertz as many data channels as we need. So then that's fine. And then we know this is just showing a schematic of like unpacking that and determining what the format of the data is. So we were successfully able to interface with the DSM 4000 to acquire data, knowing that now we could take that data and put it into a model in real time. Next. So next, what are we going to do? What is our actuator performance requirements going to be? So we did a lot of finite element modeling, and we find that the 1 to 150 model is going to have these requirements of like 1/4 inch, 5 pounds, 8 inch per second demands for that. But then the 21 to 25 model is going to have higher requirements, a little over an inch of displacement and maybe around 200 pounds and the same velocity. You know, obviously the velocity doesn't change with time scaling or the model scaling. So is there a solution for both cases? What can we find? Because they make really small actuators, they make big ones, they have different types. We have hydraulic, pneumatic, electric. These are all the different types. Obviously, FIU is not equipped with a hydraulic power system. It would be a big investment to do something like that. Pneumatic is a little bit different because you're able to get air sources and figure out, but then pneumatics and air and stability, like there's a lot of issues to deal with compressibility of air and control. They're not really good at control. So what is our best option? Electric actuators. Electric servos tend to perform very similar to hydraulics and control, but they're very reliable and stable. So you could turn on a system and electric actuators will stay exactly where you need them. You could give them a command and they'll go exactly where you need because of the built-in linear encoders. So next, yes. So finally, controller. We know the speed goat system is equipped with multiple types of IO capabilities, so it's expandable, similar to how like NI systems have their different devices. Speed goat has various different IO devices, and they have a controller for these electric actuators to control it over the real-time serial ports. Next. So we decided on a company, Ultramotion. They provided a series of linear actuators, and you could go through this, keep going until you get to the towards the end, I'll just explain. And then if you could click on that video. Does the video work? Did it copy over? All right, I'm not sure if the video actually.
Yeah.
Yeah, all right, it didn't copy when you guys copy. It didn't copy over. No big deal. That's actually just a video of the actuator working in another environment, and you would see just a different bandwidths that it could operate at. The idea of these actuators is that they have a 7-inch rod, so we're getting the full displacement that we need plus some more if we need to move the actuator underneath the turntable in a certain position. They're ball screw, so they give you really good reliability and linear resolution. So meaning like you can get very small increment changes with high reliability with the lead screw of how many turns the screw is doing around the rod. Looking at our requirements for forces, these satisfy them. We can get up to 500 pounds of force, torque movement in that, and then have very good resolution in the displacement of the actuator. So it meets our requirements for that and speed as well too. These are fairly quick actuators. And we don't need to do any external position sensing. So sometimes electric actuators, they require an external sensor for displacement to know where they are. These have a built-in encoder, so we could do that feedback positioning and know exactly where we are and maybe build in some compensation if we need to with them if we're finding that there's a little bit of sloppiness, because sometimes there's what's called backlash on an actuator if you have too much force, but I don't think in our case we're going to have any of that. So finally, and then when we move into our other phases, phase 3, 4, we're going to have to get restoring force back from these degrees of freedom. Right now, we're just looking at the wind load data coming into the system and then applying displacements. In the future, we have to have more interaction. We need to obtain restoring forces at this physical specimen. So we could retrofit these things with like Futech load cells or other types on the rod end and be able to get the better control, that full integration of the local degree of freedom. All right, and then next. I think that's it for me. Right.
One comment about the time delay issue or the compensation technique, if you'd like to comment on that, Tommy.
Okay. Yeah. So that was sort of what I mentioned with the electric actuators, is that if we're finding that the response over time is not good, we can implement these actuator compensation techniques to electric actuators as well, because we have that built-in feedback transducer. Well, I'm going to be doing some benchmarks. These are actually, in order to my facility right now to do some benchmark testing. I'm going to do some tabletop tests to see what our time delay is. and we'll see. So then we'll know how to tune the compensator right to make it work with our hybrid simulation.
Yeah, another challenge is actually the repeatability of such testing, because we need to do like different trials and compare like what happens first the trial and second trial and so on. Also at different scales, what happens at smaller scale compared to like larger scale, which means that we are expecting to see forcing function discrepancies, and that could be from the variability of the peak pressure coefficient itself. Again, the wind flow, we cannot 100% replicate that from test to test. Also some errors in sampling errors or other uncertainties related to measurements. And this is something we would like to learn in this experiment. As of now, we don't have answer for these challenges, how we can minimize the effect of these kind of discrepancies. But we'll be reporting that based on the outcomes of this experiment. And I should say the experiment is planned for this April. So hopefully by the end of summer, we can report the outcomes of this experiment. Okay, so for the all audience attending this presentation, these are some possible like hybrid simulation application that we are thinking of. And you can think about that. Come and discuss with us if you see any potential like idea that you would like to pursue. First, could be related to transmission tower system, because this is like multi-span, multi-span and long span structures. So we can think of conductors modeled as substructure, cladding systems like the one we showed today in our facility from the tour. You know, discussing the vibration and water penetration, where we can model the cladding panel as a substructure. Offshore structures, we can also think about the wave simulations, like wave shape, I should say wave shape, not the actual waves. Damping system on a tall building, like what Liang discussed. Communication infrastructure, traffic signals, and other infrastructure systems. I also would like to announce that if you are not aware of this committee, we recently established a subcommittee under the MEX, Multi-Hazard Engineering Collaboratory on Hybrid Simulation, MEX network. MEX network is led by Dr. Shirley Dyke, and I'm chairing this subcommittee on fluid structure interaction and real-time hybrid simulation in fluid structure interaction applications. The committee brings together researchers from different institutions around the world, United States, Canada, Denmark, Norway, Colombia, and we're open if you would like to join, let me know. The committee members bring expertise in real-time hybrid simulation field, wind engineering, wave engineering fields as well. And we're trying to leverage our experience and the lesson learned from different areas around the world about the techniques, the new techniques or the new methods and how we can include fluid structure interaction application to enhance our experience in wind tunnel and wave testing. I'm happy also to announce that the first committee report was published on Design Safe. I will copy this link and leave it in the chat. And I think that's it.